Dear friends, welcome to my channel. Today I am going to show you some basic examples on critical depths, so specific energy and momentum principles in open channel flow. So my name is Johannes. Let us see some examples on this topic. So first example on this chapter, critical depths and specific energy. So we are going to calculate the critical depths and the specific energy for a discharge of 5 meter cube per second in the following channels. So you have a rectangular channel with bottom dimension 2 meter, triangular channel with side slope 0.5, and trapezoidal channel with bottom dimension 2 meter and M side slope 1.5, circular channel diameter 2 meter. So we are given some discharge and also some geometric parameters, dimensions. Let us see. So the first example for rectangular channel, let us see. You have specific discharge. Specific discharge is found from this equation, Q over B, which is 5 over 2, 2.5 meter cube per second. Then YC will be Q square over G, the whole 1/3. So this is the specific energy of a rectangular channel with a discharge of 5 meter cube per second and bottom dimension 2 meter. So since for rectangular channel, this is just the specific energy versus YC ratio, which is 1.5, or just YC is just 2 over 3 of AC, or AC is 3 over 2 of YC, so AC will be this one. So this is the specific energy, which is critical, 1.29 meter. Now let us proceed for triangular channel. For triangular channel, again, you have this formula, 2Q square over GM square, the whole 1/5. So this is the geometry of triangular channel with apex angle theta and 1 to M side slope. Then for critical flow condition, already we derive from this equation, Q square over G is equal to A cube over T. Then area is my square. Then since it is cube, then M cube YC. Then if you rearrange this equation, you get this is the general equation for critical depth calculation for a triangular channel. Then if you substitute the given parameter, you get critical depth 1.828 meter. Then since for triangular channel, you have 5 over 4 of just 5 over 4 times EC, just 4 over 5, or 5 over 4, 1.25. Then you have EC is just 5 over 4, just crisscross this one. So you have, this is the critical specific energy for a triangular channel. So for trapezoidal channel, using table 2A, the corresponding value of this one, which is phi, which is QM 3 over 2, the power of 3 over 2 over square root of G, be the power of 5 over 2. If you substitute, then you get this result. Then for this value and for the side slope given, what will be eta C? So eta C can be found from table. So how do you get this eta C? So eta C, let me show you the table, which is this one. This is the table for circular channel and trapezoidal channel critical depth calculation. So let us see for trapezoidal channel. So for trapezoidal channel, you have eta C already. You compute how much? Eta C 0.51843. So 0.5843. 5183. So eta C 0.5183, you just search from this one. 0.5183 is around here. So you have 0.5183 here. Then what will be eta C? So after this, just you take this one. So eta C will be 0.536. Then just crisscross from this. Then you can find YC, which is 0.715. Then finally, you can find the critical area. The critical area B plus MYC times YC. Then if you substitute that, you get this is the critical area. Then critical velocity will be the discharge divided by critical area. So you get this result. Then V square over 2G will be this one. Then finally, you go to specific energy, critical specific energy will be, just you substitute the above values, then you get 0.979 meter. Okay, using calculator, let us using calculator for a trapezoidal channel. Just we know this one, which is for critical flow, Q square T over G A cube is equal to 1, or A cube over T. Q square T over Q square over G is equal to A cube over T. So if you substitute top with this area, then you have, this is for iteration using calculator. So put the given parameters, Q given 5 square times 1.5 cube divided by 9.81 times to the power of 5, since bottom dimension is given. Then only eta c is unknown. So eta c we will have, this is the value, which is the equation, the expression. So you multiply both sides by the exponent 1/3. So the reciprocal of these exponents, if you multiply by 1/3, then you can find eta c. This is eta c. So get eta c from this one, then we get this equation. So this is the general equation, which is for iteration purpose we will use. So this is just the result of this expression will be 0.2687. So this is numerator multiplied by crisscross, just crisscross 1 plus 2 eta c, then divided by this expression 1 plus eta c, the whole cube. Then you have to close this bracket. Then once you close this bracket, then you just open your calculator, then you type any number, say for example 0.85, you type, then equal, then just if you check answer, then answer will be saved, which is 0.85 will be saved in your calculator. Then make your calculator on. So if you make your calculator on, then write the following expression, this one, without any equal sign, just cube root of, you can see in this calculator, if you write cube root of this one, be careful on brackets. So if you miss one brace, it will not be okay. So let us see cube root of bracket, which is the whole bracket, which is 0. Just numerator again, you have to close the bracket, 0.2687 multiplied by 1 plus 2 times answer. You just click answer in your calculator, you have answer here. Let me show you answer in your calculator. Click answer in your calculator, which is this one. Just click this answer. We just click this answer in your calculator, here answer. Already you have saved 0.85. Then if you click, the first iteration will be 0.4485746. Again, you click equal, you get second iteration, third iteration, fourth iteration, the fifth iteration. Then finally, this will be constant. So this is your result, which is eta c, which is the unknown result. Then once you find eta c, then you just crisscross here. Then you can find critical depths. So let us see. Once you have 0.5356 from eta c, this one, the critical depth will be, just you multiply, then finally 0.715 meter. Either from table or using calculator, you can choose. So the choice is just depends. So this is the area. You can calculate again as usual. Then critical velocity Q over area. You have, this is the velocity. Then finally you have just critical specific energy YC plus VC square over 2G. Then you get this result. Same result as previous we were using in just table. So 0.979 meter. Then the fourth problem is circular channel. So for circular channel, we will use, this is just critical flow condition. We can apply this one. Just section factor for critical flow condition for circular channel is Q over square root of G. So once you find this one, then this result should be substituted to this one, ZC divided by D to the power of 2.5. Then once you get this result, then from section factor, just this section factor formula, then from table again showing section factor divided by D to the power of 2 over 5 versus this one, the corresponding value of Y over D, just by suitable interpolation method, you have got this one. So YC will be this one. Let me show you the table again. Let us see the table. Let us see the table, which is how much? This one, 0.2822 for circular channel. If you go to circular channel, this is 0. This is for circular channel section factor for critical flow depths. Then Y over D will be, just read out, 0.28, this one. You see, this is the location, which is this one, Z divided by D the power of 2 over 5 or 2.5 or 5 over 2. Then what will be, by interpolation, you can find this one. So this is already known, 0.281. Then you can just calculate. So once you have 0.2822 from the table, then from table to A1 showing this one versus this one, then you read out this. Once you read this one, then crisscross. Or diameter is given, then critical depth will be this one. So you can find the angle subtended by the water surface, which is the critical angle, 2 theta c. 2 theta c, which is 2 cos inverse of 1 minus 2 yc divided by d. You can compute 2 yc. Again, either using calculation or using table, you can read out using the same approach. Let me show you. Just the angle subtended by water surface in radian measure. You can convert into radian. So the second column will be this one. So this is in radian measure, 3.228 something. You can find 3.28 something. You can find. Then once you have this, then the angle subtended by water surface will be computed. So you see, just let us see. Once you have this one, A critical divided by D square, again you can compute, which is this one. This is the table. This is for subtended angle. Then any geometric parameter will be computed here. So critical area, you can find then specific energy will be, just once you have critical velocity, Q over area will be the velocity critical. Then critical specific energy will be this result. So I think this is circular channel. So as the exercise shows that the critical specific energy for circular channel is given by this equation. As the exercise, we can just prove this one. So 2 alpha is the angle subtended by the water surface. Then D is the depth of water. Then you can just check. Okay. Second problem is, let us see alternate depths. Example 2.2. So a rectangular channel 2.5 meter wide has a specific energy of 1.5 when carrying a discharge of 6.48. Calculate the alternate depths corresponding to the four numbers. So you have this specific energy formula. General equation for specific energy is this one. Y plus b square over 2g is equal to y plus, in terms of discharge, q square over 2g b square y square. Then if you substitute, then y is the unknown value. So if you just rearrange this one, take common factors, then finally we have this equation. Then y take out from y cube, take out y is equal to q root of 1.5 y square minus 0.34243. Then again you type in your calculator this one, but give any number, any arbitrary number in your calculator. Then you will iterate accordingly. Then you type this one with answer. Then by iterating for any value of y, which is any arbitrary value will be given. Then finally you have two values will be changing constantly. So y1 will be 1.296 and y2 will be 0.625. So solving this equation, then finally the full number will be computed. Full number is for rectangular channel only V over square root of Gy. So the hydraulic depth for rectangular channel is known as area divided by top width. Area divided by top width. So this will be, this is B times Y, B times Y divided by top width is equal to the bottom dimension. So you cancel this, then it will be Gy. So this is for rectangular channel. Otherwise, for other channel, you have to substitute this equation. This equation should be substituted. So substitute the given parameters. Velocity is already known. Then finally, you have y. Then if you substitute y for y1, 1.296, f1 will be this one. Since it is less than 1, so it is just subcritical flow. Subcritical flow. And for the second depth, 0.625, you have supercritical flow. Okay, example 2.3. A flow of 5 meter cube per second is passing at a depth of 1.5 meter through a rectangular channel of width 2.5 meter. The kinetic energy correction factor alpha is found to be 1.2. What is the specific energy of the flow? What is the specific energy of the flow? What is the value of the depth alternate to the existing depths if energy correction factor is 1 is assumed for the alternate flow? Simple. So you are given this parameter, then you simply just calculate V1 Q over area, then you get this result. Then alpha 1 V1 square over 2G, you have this is the result. Then finally you have to compute now specific energy E1 Y1 plus alpha 1 V1 square over 2G. Then you get this result. Then for the alternatives Y2, then specific energy is already calculated, then what will be Y2? So Y2 by try and error, you can use calculator. Again, rearrange this equation by taking common factor, then find Y2. Then you can just calculate using iteration, using calculator, 0.413. Okay, as exercise, you can try this problem. A rectangular channel, 8 meter wide, conveys a discharge of 15 meter cube per second and a depth of 1.2 meter. Calculate the critical depth, critical velocity, critical slope, and minimum specific energy. So for rectangular channel, already we have formula, which is YC is equal to Q square, small q square over G the whole 1/3. Already in the previous discussion, I think we have seen these formulas. These formulas, critical depth for rectangular channel. You can see this is the formula for rectangular channel. So you have Q, B, then you can substitute here. Then finally, we can arrive at the solution. For rectangular channel, already we know the formula. Then we can compute. So I think Q is given. Then first you can find small q. Small q will be capital Q over D. This is discharge intensity divided. Discharge intensity is given by total discharge, which is given small q, which is this one. Then finally, you can find critical depth. Critical velocity, VC square root of G for critical velocity, G times D, or for rectangular channel, D is area divided by top width, then Gy. So once you find YC, you substitute here. Then critical slope again, already you have critical velocity, then you have Manning roughness and slope, then you can apply the formula. State whether the flow is subcritical or supercritical. If you don't have any, if it is not at critical state, what will be? Determine the conveyance and section factor again. You can calculate. So I think this is enough for today. So I will continue momentum application in the next slide. Thank you very much. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know. And thank you very much.